Hey, what's going on, everybody? All right, so we've got chapter 11 here in our statics book. Let me go ahead and just kind of get this situated. All right, so for the problems in chapter number 11, we've got 4, 9, 14, 15, 17, 21, 24, 46, 57, and 65. So I'll go ahead and get started here. Number 4, where's problem number 4? Number 4 wants us to find the modulus of elasticity, modulus of rigidity, and the Poisson's ratio. We're just saying modulus of elasticity, modulus of rigidity, and Poisson's ratio are interrelated. They want us to calculate G for E being 30 million psi and mu being 0.3. And then also they want us to calculate mu for an E of 16 million psi and a G of 5,800,000 psi. And this one is fairly straightforward. Just got to do a couple of calculations here. Let me forgot to get my stuff here for my. All right, here we go. That's better. So number 4. Again, this is just a quick calculation. We've got G, what they want us to solve for. And then G is just going to be equal to our 30 million. Divide that by 2. And then 1 plus 0.3. And that's going to equal, let's get my calculator here real quick. So 30, 1, 2, 3, 1, 2, 3. Divide that by parentheses, another parentheses, 2 times 1 plus 0.3. Close that, and then close that, and close the division. And I get 11,538,461.54. And then for our mu value, we want to do 16 million. And then divide that by 2 again, 58. And we get 16, 1, 2, 3, 1, 2, 3, divided by parentheses, 2 times 5, 800, 1, 2, 3, close parentheses, and then equal 1.3793. I'll just go that far there. And sorry, this will be psi up here for our rigidity value there. All right, and next we have number 9. And number 9 says a concrete roadway pavement is placed in 60-foot long sections. An expansion joint between the ends of the sections is established as ½ an inch at 70 degrees Fahrenheit. Calculate the width of the joint at temperatures of 30 degrees Fahrenheit and as well as 110 degrees Fahrenheit. So one thing that we do know, we know the length. I'm just kind of doing a couple of my known values here. We know the length being 60 feet. And at 30 degrees, we have a change in temperature of -40. So from 70 to 30, get -40. And I'll just come over here at 110 degrees. We have a change in temperature of actually +40. So +40 there. And again, that's just from 70 to 110. for our lambda value there, LT. So therefore this is equal to 6.5 10 to the negative 6. L was at 60 value there, but we make sure we times it by 12 so that we put it in inches or whatever. And then lastly was our delta T, which was our 40. And so we get a value of 0.187 inches. Sorry, not 0.187, sorry. 0.1584, and this over here is not 6.5. This is not 6.5. This is actually 5.5. Sorry. Alright, so then we can do the same thing over here. It's on a lambda for the 110, which actually would be the same thing, because yeah, everything else stays the same. This is still going to be the, and then our length doesn't change either. The only major difference is that the 40 is a, and I actually forgot to put minus here. That should be a negative value over here. Only difference is that lambda is now a positive 0.1584. And so the gap here is just going to be 0.5 plus a 0.1584, which is going to give us a value of 0.6584 inches. And then for here, it would be basically the opposite. This would be 0.5. Again, this is, we're dealing with the gap here. Be 0.5 minus 0.1584. And so therefore we get 0.3415 inches. And I'll scroll down here so that we can do number 14. And number 14 says that a 5.5 inch by 11.5 inch Douglas fir column and a hem fir column of the same size are bolted together to form a short composite column as shown. What portion of a total load of 70,000 pounds will each material carry? So number 14 we have here, I think they're the same size, so the area of DF is also equal to the area of HF material. Doesn't really matter in this case for the area. So we got 11.5 times a 5.5, and so therefore we get 63.25 inches squared. Now for the E value for Douglas fir, we're using 1700 KSI for that, and I'm gonna just come over here for the E value of the hem fir. We're using a value of 1400 KSI for that, and so therefore our Ngon value is E divided by E, and that gives us 1.2143. So therefore, if we plug that back into our equation, we're getting something looks like that. And so therefore we already know our N value again, so that would just be 1.2143 times that stress for the hemp or the Hemfer, and then P is equal to the area times that stress for DF plus the area stress HF, which they give us P. They say it's a 70-pound load. So that's 70,000. And that's going to equal to, we know the A for this one. A for both of them actually is 63.25. And then we can multiply that by our sigma there. And sigma is sigma is the 1.2143 sigma HF. And then we can just add that to our 63.25 sigma HF. So now you can see here we have like terms, sigma HX, sigma HF. I'm going to scroll down a little bit here. And so therefore, if we just revamp this equation a little bit to get sigma HF by itself, we therefore get a value of 500 psi for that. So the amount of force just for HF alone would just be our A times sigma, which is just 63.25 times the 500, and we get just calculate that real quick. 63.25 times 500, we get a total value of 31,625 pounds. And then it'll be real quick and easy to find PDF. PDF is just equal to the total P minus that PHF, which is 70,000 minus 31,625, which gives us 38375. Alrighty, that was 14, so we can go to 15. And what is 15? 15 says, for the short column shown, assuming the lateral buckling is prevented, calculate the magnitude of the axial load P that will cause the total length of the member to decrease by 0.01 inches, and then calculate the compressive stress in the steel. So let's get this image drawn here. All right, so we've got this here, and we got to calculate the magnitude of the axial load first. I think the only additional thing that we may need is our E values, which I already have that. E for the steel is 30. And then E for the cast iron is 15. And so therefore we can use our equation here, PL over AE. We've got P, or no, we're trying to solve for P. We're trying to solve for P. We know L, we know A, we know E. Same for the cast iron. We know L, we know A, we know E. We're just trying to solve for P. And we also know our lambda value here, which our lambda, they said it changed from 0.01, right? Yeah, 0.01 inches. So therefore, plugging in our values here, and then trying to solve for P, we get our equation. It kind of looks like that. And then solving for our P, we get 49.1 kips there. And then for our stress, this is part B. This would be part A, sorry. That would be P over A. And P, we solve for 49.1. A, area, we just got 4 for that. 4.0. Because they only asked for the compressed stuff in the steel, and the steel area was 4. Yeah, so that's 4.0, and so therefore we get 12.28 KSI. All right, so that's 15. Next is 17. Number 17 here, and 17 says a long flat steel bar that's 13 millimeters thick and 120 millimeters wide has semicircular grooves as shown and carries a tensile load of 50 kN kilonewtons. Determine the max stress in the plate if R is 8, R is 21, and R is 38. But what's R? Well, let's just draw the image first so that we can kind of see everything. And of course, that's not drawn to scale. We've got, that's not what I wanted, 120 mm, right? And then our forces, I'm gonna just put P there. And I got more room here, so I'll just put P equals 50 kN. I think it's 50. Yeah, 50. And then R is actually gonna be, whoops. Right there. Alrighty. So yeah, so for this one, they want us to do three different R's here. So if R is 8 millimeters, we definitely do need our K value. So we'll need to do our R over D, which would be 8 divided by 104. And then our max here is just going to equal to K P over A. So looking in the figure the little graph there, 11.14. This graph here, I guess we can say that K is like 2.4. So we'll say K is 2.4. We got 50,000 newtons here for that. Divide that by A, which A, we didn't really do A yet, so let me grab A here, which would be the 13 times 120 minus 2 times 8. And that gives us an A value of 1352 millimeters squared. So that's 1352. And so therefore we get 88.8 megapascals. So B now has a R value of 21. So therefore the RD is now 21 by 78, which gives us a 0.27 R value, our R over D value. And with 0.27, we will say that our K, let me write this, K, let's say 0.27, I'll say about 1.85 on that. And if you're not familiar where I'm getting D from, hopefully you're looking at the graph and all that, but D is just basically this information here. So that's 1.85 there. So therefore our area also changes. So what's our P stays the same though. P is still 50,000 newtons there. Our area though, I'm gonna just drop in area here. That becomes $1014. And so therefore we get 91.2 megapascals for the stress. And then lastly C, which is 38 millimeters. Again, we'll need A for the area, which will be 13 by 120, and then subtract out these guys here by 38. And so therefore the area is 572 millimeters squared. Our R over D, we still need that, so we can locate our K value. And so therefore we can use that information to find the max tensile stress here. Let's see, K value 0.86. I'll say K is 1.25 times that 50,000. Divide that by the 572 equals a 109.3 megapascals. Alrighty, that was 17, so 21. Problem number 21 says a prismatic bar 50 millimeters by 75 millimeters in cross section is subjected to an axial tensile load. Compute the max shear stress computed in the bar. Compute the shear stress and the tensile stress on a plane whose whose normal is inclined at 70 degrees to the line of action of the axial load. So if I were to draw this out, whoops, do that the wrong way. And then they said that these were 50, right? Alright, so for the first thing that we'll need to do here, let me actually drop this down. First thing that we'll need to do here is solve for our tau max tau prime max here. That's going to be P over 2A, which is equal to 50,000. Divide that by 2A, A being 50 by 75. And so therefore we get 6.67 megapascals. And then when we arrange this to where we, for B, we need to arrange it so that we have a 70-degree incline there, right? So we have something like that. That's 70 degrees there. My 7's kind of out of whack. There we go, looks better. And so therefore our tau is going to equal to P 2A sine 2 theta, which will get 50 divided by 2. Area was the 50 times 75 millimeters, right? And then sine of 140, which gives us 4.29 megapascals. So therefore that stress there is going to equal to P over A cosine squared theta, which gives us 50, and then A being again, or this is time, sorry. And so therefore we get 1.56 megapascals. All right, that was 21. 24. For 24, all we have to do is sketch the element and show the shear forces, and then determine the tensile normal stress on a plane at 35 degrees with the horizontal. Show this plane on the sketch. And it's an element and a member is subjected to a pure shear of 10,000 psi. So essentially you just had to do a quick sketch on here. And I'll just sketch this out, something like that, nothing too crazy. We can say that this is going that way, that's going this way, this is going that way, and therefore this will go this way. Remember, we're trying to do couples. And they're saying that the this is 10,000, yeah, 10,000. So this would be 10,000 times W, and then this one would be the 10,000 for the height, and then 10,000 again for the width there. And then lastly, another 10,000. Hopefully I got enough space for the, did I make it? Yeah, there we go. All right, and then for B, they said to determine the tensile stress on a plane that's 35 degrees and horizontal from the horizontal. So if I was to draw that, I would probably do something, I don't know, something like this. And then for this, theta. And then I could solve for this by just doing tau sine 2 theta. This gives us a 10,000 sine 70, which gives us 9,400 psi. All right, 46. 46. A horizontal steel member is anchored at each end. A horizontal steel member is anchored at each end. Just prior to installation, it was heated. After anchoring, it was allowed to cool to 20 degrees Celsius, at which time a stress of 70 megapascals developed. If the member is 3 meters in length, to what temperature was it heated to have developed this stress upon cooling? So 46. So let's see, so we got to do the change in temperature to cause a stress of 70 megapascals. So we can use equation, the three kind of modify equation here, E sigma, or alpha, I think it's alpha, right? So therefore we know that stress there is at 70. And we know this E value for this material is 207 10 to the third, and then the alpha value there is 11.7 10 to the -6. And so therefore we have 28.9 degrees Celsius. And so they said it was allowed to cool to 20 degrees Celsius, so therefore it wants to know where was it heated. So the change of temperature was 28. It was allowed to cool to 20. The change in temperature was 28. So therefore it would be 48.9 degrees Celsius. So this is kind of like a initial plus the change equals the final. All right, so after 46 we've got 57 here, and then after this we just got one more. 57 says that there are 3 1/4-inch diameter wires that are symmetrically spaced and are 20 feet long as shown. The outer wires are steel and the middle wire is bronze. The wires support a rigid horizontal steel box weighing 2,000 pounds. And he wants to calculate the stresses in the wires and the elongation of the wires themselves. I'm actually going to draw this out here. So we've got this. We've got 1, 2, 3. And then we've got a box here, and this is just going to be a funky looking box just because I have never used this color, so we're going to use it now. Then I said we have steel, we've got bronze, and then we've got steel. And the height of this is actually going to be 20 feet. And then the load, or 2,000 pounds, sorry. All right, so from there, that's what, 57, yeah. So from there, what we would end up having to do, let's get my sheet here. And actually this is a 1/4 inch diameter, so therefore the area of this is the 0.49 inches squared. So up first we have some of our forces in the y direction. That's going to be equal to 2 times our steel, and then 1 for our bronze. We only got 1 bronze and 2 steel, and then minus our 2,000 that's pulling down there, and that's going to be in equilibrium. From there we can solve for our change in length for our steel. That's going to be the same change in length for the bronze. So this is PL over AE being equal to PL over AE. I'm actually going to throw these in here just so that we keep them the same, like that. And then so therefore we don't know our P, but we do know our L, which is our 20. Of course it's in feet, so we got to put it in inches. Then divide that by our A, which is the 0.49, 30 million. Then we get P for the bronze. And then we get 0.49 times 12 for our bronze there. All right, so now what we can do, I'm going to actually scroll down slightly here. Now what we can do is kind of plug this back into our previous equation there, that first equation that we had. So we can say 2. Well, actually, let me actually solve for one of these first. That way we have 2 equations and we can plug back in, because that'll make it easier instead of plugging the whole thing in. So we'll do the steel, and in order for us to do that, we'd have to bring our 0.49, 30 million over to the other side, multiply all that stuff there, and then divide that by the 20 and the 12, and then we end up getting 2.5 P bronze. Yeah. And then for our equation here, we got 2.25 P bronze. That way we can have a single unknown. Solve for a little bit better. P bronze by 2,000 pounds. And then once we solve for our P bronze, we get 333.3 pounds. And so therefore our steel here is 2.5, 333.3, which gives us 833.3 pounds there. And now we can actually calculate our different stresses. Stress for the steel, or no, sorry, stress for the steel is 833.3.49, gives us 17,010 psi. And then for our bronze, it's 333.3 by that 0.49, and we get 6,800 psi. And then B, only want the steel value here, so we get PL over AE, then we got sigma L over E, because PA is just sigma, right? And we know what sigma is now. Sigma for the steel is the 17,010 psi. L is 20 multiplied by 12 to throw it in inches. E is still the 30 million. And therefore we get 0.136 inches in elongation there for the steel. If you want to, you can do the bronze, but we don't necessarily have to. And then lastly, we have 65. And 65 says a short timber compression block of rectangular cross section 150 millimeters by 200 millimeters has the allowable compressive stresses of 6 megapascals and an allowable shear stress of 1.6 megapascals. Calculate the allowable load that may be applied to the member. So first we have A here being 150 by 200. That gives us 30 times 10 to the negative 3 meters. If we left it in millimeters, it would be 10 to the power 3, but we jump it in meters, so 10 to the negative 3. Then we can say sigma C, the allowable, right? Allowable, it's going to be 6 megapascals. And that's going to be, 10 to the 6 pascals. And then our allowable that one there, tau, sorry. And that's just 1.6 megapascals also, so it's just 1.6 times 10 to 6 pascals. So now we got everything in the right units. We can say our max force here times A, and that's 6 times 10 to the 6 times 30 times 10 to the third. This gives us 180 times 10 to the third newtons. And then if we do our shear stress, we'll say P2A for the max there, sine of 2 theta, sorry. Sine of 2 theta. We would say, and this would be our max force, right? So P max, based on our shear here, would just be our tau by 2A divided by sine 2 theta. And that gives us 1.6 times 10 to the 6 times our 2, and area was 30 to the and then divide that by the sine of 90 degrees. Yeah, it's just a block there, sine of 90 degrees. And then I'm not going to scroll down, I'll just right over here, we get 96.0 times 10 to the third newtons. Alright, so that is it for chapter 11. Hopefully that helped you guys out. Definitely let me know if you have any questions. And then stay tuned for the next one.